Hi there, so this is for Jasmine. Which of the following provides the greatest energy? And we have 5 choices. This is actually like 5 little problems, and we're going to need to calculate energy for each one, and then whichever one is the greatest, that's the answer. So we're going to use 2 equations. We're going to use this one, in which we have wavelength times frequency equals c, speed of light. And then this one, we've got frequency times Planck's constant equals energy. So those are our equations. These are our constants. So here's speed of light, and here's Planck's constant. So this is in meters per second, and this is in joules times seconds. And then we're going to need one conversion for this, and that is when we go from nanometers to meters in B and in D. So 1 meter equals 10 to the negative 9 nanometers. Okay, so now for the first one, they give us the number of photons and they give us a frequency. So down here on A, we have our frequency and we have the number of photons. So since we have our frequency and H is a constant, we can calculate energy. So we're going to use E equals HV. So H is our Planck's constant, and then V is our frequency. Frequency is always in 1/seconds, which is also hertz. All right, so you multiply those two and you get the energy. But the thing is, this is the energy for 1 photon, and we have many more photons. So if this is the energy for 1 photon, you can think of this as 6.63 times 10 to the negative 25 joules per photon. Okay, so we're going to take the number of photons we have, and we're going to multiply by the joules per photon, and that gives us this number of joules. And the thing is that photons here, which is understood to be in the numerator, cancel out with photons here, which is in the denominator. And the reason this is understood to be in the numerator is you can turn anything into a fraction by putting it over 1. So for this first one, we have this amount of joules of energy. Okay, so the second one, B, they give us photons and they give us wavelength. So we've got this amount of photons, this amount of wavelength in nanometers. So I'm trying to get to where I can use my right hand to point out things. Okay, so they gave us wavelength. This little thing is the symbol for wavelength, and it's in nanometers, and then they give us the number of photons. The very first thing we're going to want to do is convert our nanometers into meters. So we start out with nanometers. That means we're going to multiply by a fraction, and down here in the denominator, we're going to have nanometers. Nanometers in the understood numerator cancel with nanometers in the denominator, and that's what we're going for. And then we want to end up with meters. And up here we had our conversion of 1 meter equals 10 to the negative 9 nanometers. So the 1's next to the M here, so we're going to put the 1 next to the M here. And that leaves 10 to the negative 9 next to the nanometers. Okay, so then we've got 550 times 1 divided by 10 to the negative 9th, and 10 to the negative 9. And that gives us this number, 5.50 times 10 to the negative 7. The nanometers here cancel with the nanometers here, leaving us with meters. Okay, so we are going to use this first equation because they gave us wavelength. So, you know, the place that I got this equation from, I don't know why they gave it to you this way. I'm kind of hoping your textbook gives it to you this way, but just in case it doesn't, you've got speed of light equals wavelength times frequency, and we want to get frequency alone, but it's multiplied by wavelength. So we're going to do the opposite of multiply by wavelength, and we're going to divide by wavelength. But what we do to one side, we have to do to the other side. So we divide the other side by wavelength. Okay, so on the right side, our two wavelengths cancel out, and that just leaves us with frequency. And on this side, we've got our speed of light over wavelength. And in this step, I just switch it around so that it looks the way I want it to look. So we had calculated our wavelength here. It started out in nanometers, and we ended it in meters. So we're going to plug that in right there. Speed of light is a constant from up here. Okay, so we plug in the speed of light constant divided by the nanometers, or sorry, the wavelength that we calculated up here from converting. Divide that and you get the frequency. And I won't go into detail, but this meters cancels with this meters, and it leaves us with 1/seconds, which is what frequency gets measured in. So the next equation is the only other one we were given here in this little set, is energy equals Planck's constant times frequency. Planck's constant's a constant from up here, and we used it a little while ago. Sorry if this is making you dizzy. Okay, so Planck's constant, and then the frequency that we just calculated goes in next. So you multiply those two like we did for A, and that gives you the amount of joules for one photon. So that's the same as saying that many joules per photon. But we don't just have one photon, we have a lot of photons. So we're going to take the amount of photons and multiply by our joules per photon. And these photons cancel just like before, numerator, denominator, and that leaves us with this amount of joules. So we have joules for A and joules for B. All right, now rather than going through it, I think what I'm going to do is say, why don't you try doing C and D on your own, because C is just like A and D is just like B. And you can let me know what you get. And E is going to be like D and B, except you don't have to convert from nanometers to meters. All right, good luck, and message me, text me if you need help.